So for today's podcast, we are looking at natural logarithms. When we were studying exponential functions, we saw that any positive number could be used for that multiplying factor. We saw down here that this x, the number we plugged in there, it could have been anything really. Now, depending upon what the problem was we were looking at, we had this a, or I guess that x value, it could have been greater than 1. It could have been 2 or 3 or 4, and that would have created this graph of exponential growth. If that factor was less than 1, like a fraction, and we saw some fractions or some decimals in there, then that created exponential decay. But we've seen a bunch of different numbers that sit in that spot. Then we looked at a few specific cases, and we talked about bacteria growth, and we said that it has to grow. So the number we're going to put in there for x, we want to pick something bigger than 1. And it was decided that we would use 2 because we wanted to think of bacteria in terms of doubling time. Because when bacteria reproduce each other, they double themselves to 2 to 4 to 8 to 16. So using a base of 2 made a lot of sense for us in terms of the model. Then we looked at what we called radioactive decay. And we decided that we have to figure out a way to measure how things decay or how things sort of disintegrate on an atomic scale. And we decided to use this idea of half-life. And we said, how long does it take an object to essentially disintegrate into half of its mass? So we decided to put 1/2 in for that factor, and that was okay. Now, as it turns out, there is actually another value or another number or another base that's very useful when we're modeling systems that occur in the natural world. And that number was discovered by someone named Euler. So it's called Euler's number. And to represent it, they took the first letter of his last name, and we use this letter E, which represents this special number that we're going to use as that new base. And it turns out E is equal to now 2.718 and so on, which we see is kind of similar to another number we've seen, pi, which was equal to 3.14 and so on and so on and so on. Pi was an irrational number, and E is also an irrational number, but we can still use it in our modeling. Now, just like with pi, we remember 3.14. With E, we're going to remember it down to 3 decimal places. So we're going to use 2.718 to represent our base for E. Now, some calculators actually have an E button, just like some calculators have a pi button. So depending upon what you have, you can either use the E button or you can just put in 2.718. If we were to draw an exponential graph with base E, it's similar to what we've seen in that here's our function f of x with our base of e to the x. It's obviously bigger than 1, so it's going to typically represent exponential growth for now, which is okay. And the same thing holds true before. E to the 0, like anything to the 0 is 1. So it goes through this spot 0, 1, like all of our exponential models have gone through so far. Now, as we've seen, this idea of a common log, we always used a base of 10. And this natural logarithm, so we're going to call it a natural log, is going to use a base of e. And since this log is used so often, we're going to give it a new symbol. So if we have log of e, so log, no longer base 10, common log, it's log of e to the x. We're just going to rewrite that as ln x. And the pronunciation of that is like, the lawn on your front yard, I guess. So ln is how we say that, ln ln x. And it's just, whenever you see ln, it's really just implying it's log base e. So that's what ln is. Now on your calculator, you do have that log button, and you also have that ln button beside it. So you should see both of those there. A few properties here we can see with these natural logarithms. If we have ln of e to the x equals x, this is one of these properties. Okay, why it works, of course, is ln, of course, is log e. So log base e of e to the x, we know that kicks out this value x. Okay. Another property we've seen, e to the ln x is equal to x. Well, that works sort of the same way. If we have e to the log base e of x, we know that's going to be equal to x as well, because the e and the log e negate each other operationally. The last one's probably the most interesting. Ln of e is equal to 1. That helps us in our calculations sometimes. That illustrated, that's just log e of e, obviously there's a 1 sitting there, is equal to 1. And we've seen this property before as well. So we're going to use this a little bit in our calculations. So let's try an example here. The population of a bacteria culture as a function of time is given by this equation. And what we see here for the first time is our factor, our multiplying factor, is written in terms of e. Now it's interesting actually for bacteria, because before we had a doubling period, and we see that e is just a little bit beyond that. It's 2 point something. So it's kind of just a little more rapidly duplicating itself quicker than just doubling. Okay, just a little bit higher, and that's the way it ends up in nature, actually, which is interesting. So here's the function. P is going to be the population after t days. So just a couple basic questions with this that we can work through. State the initial population. So we see here the initial value, the initial population is just 200. Just taking that right from the equation. We could also work that out. We could plug into our function the population at 0, which would equal 200 times e to the 0.094 to the 0. 0.94 to the 0, of course, is 0. E to the 0 is 1. And of course, 200 times 1 is just 200. So you can get that right from the equation, or you could actually work it out and see it. We'll probably just take it from the equation for now. B, you want to estimate the population after 20 days. So for this, that means find the value of the population when t is 20. So p at 20 is equal to our initial value, 200e 0.094 to the 20. Now you should be able to, you should try this on your calculator. Just take a second, you can pause the video, see if you have an E button, or if you don't, you can use 2.718 as our value. Okay, when you plug that all in, you should get 1,310, somewhere around there. Okay. Third kind of question, how long will it take the population to triple? So for this, if we're starting at 200, then to triple, it's just 3 times 200. So the population should end at should become 600 is equal to 200 e to the 0.094 t. I'm going to divide both sides by 200. That's my first step. These divide out. That leaves me with 3. It's equal to e 0.094 t. Now to solve this, I have to get that exponent down, so I'm going to impose logarithms on both sides. You can impose a log, or you can impose a ln on both sides. It doesn't matter. You get the same thing anyway. So I'm going to ln both sides. I'm going to swing that exponent down. So I'll have ln 3 equals 0.094t ln e. And this is nice, actually, having this ln e here, because we know ln e is just equal to 1. So that is just going to become 1, which is great. And to solve this for t, I just need to take ln 3 and divide it by 0.094, just like I did with both sides here. 0.94 divides out, and that leaves me with just t equal to, just use your calculator, and you should have that ln button, ln 3 equals, divided by 0.094, around 11.7. 11.7 days will give it to us. Okay, and again, an approximate value, we should write t, we've seen this squiggly equal sign, so about 11.7, and I think we've seen the textbook write this as, I think there's a dot above it and a dot below it, 11.7. That's how we're going to represent an approximate amount. And a little more interesting, how long would it take the population to reach 1 million? So same idea here. We're just going to plug in 1 million for our value of our population. 1, 2, 3, 4, 5, 6 is equal to our initial value, e to our exponent, 0.094t. Okay, obviously step 1, divide both sides by 200. Divide by 200, divides out. Grab your calculator. 1 million divided by 200 is 5,000 equals E094t. Same thing, I'm going to impose a ln on both sides. I'm going to swing the exponent down, 0.94t. Ln of e, again, ln of e is 1, which is great. That becomes 1. So I'm going to divide both sides by 0.094. 0.094 divides out. T equals ln 5,000 divided by 0.094. Around, I should make that squiggly line, sorry, squiggly. Let me start again. T, squiggle line, 90.6, okay, days. All right, that's it. Try those homework questions, and any questions, let me know.